You think you know what aliens look like. Hollywood sells you sleek ships with blinking lights. Science fiction feeds you the obvious. But what if real alien technology hides in plain sight? What if it spins like clockwork, follows impossible orbits, and arrives exactly when it needs to? On July 1st, 2025, the telescopes in Chile spotted something that shouldn't exist. A 20-kilometer object racing through space at 245,000 kilometers per hour, coming from the direction where our galaxy's oldest stars live, moving on a trajectory that defies coincidence. Its spin rate, exactly 16 hours, 16 minutes, too perfect, too controlled, too artificial. Meet 3I Atlas, the third confirmed visitor from another star system, and according to Harvard astrophysicist Avi Loeb, it might be watching us. If you value documented space discoveries like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. This script is researched and factual, using sources from Harvard University's Black Hole Initiative and the Initiative for Interstellar Studies, published in July 2025, and NASA's Jet Propulsion Laboratory Orbital Mechanics database, updated September 10th, 2025. These aren't tabloid claims. These are peer-reviewed calculations that will make you rethink what's possible. Now back to the information. July 1st, 2025, 445 astronomical units from the Sun. That's 670 million kilometers out beyond Jupiter's orbit. The asteroid terrestrial impacted Last Alert System telescope in Rio Hurtado, Chile picks up a moving dot, magnitude 18, barely visible. But something's wrong with its motion. The trajectory doesn't curve like objects bound to our Sun. It cuts straight through space like a bullet. Hyperbolic orbit. Eccentricity 6.141. That means it's moving so fast it will never return. Within hours, follow-up observations confirm the impossible. This object came from outside our solar system. Not just outside, from the thick disk of our galaxy where stars are 7 billion years old, twice as old as our Sun. Marco Micheli from the European Southern Observatory and Davide Farnocchia from NASA's Jet Propulsion Laboratory run the numbers. The math is clear. This visitor has been traveling through interstellar space for millions, possibly billions of years. But here's where it gets strange. 3. I-Atlas isn't wandering randomly through space like a cosmic stray. Its orbital plane sits within 5 degrees of Earth's orbit around the Sun. The probability of that alignment happening by chance? 0.2%, a statistical near impossibility that Loeb calls an exceptional coincidence. The object measures 20 kilometers across based on its brightness and lack of visible tail. That makes it 100 times larger than the first interstellar visitor, 1I Oumuamua, and 10 times bigger than the second, 2I Borisov. Finding an object this massive from interstellar space should be incredibly rare. We should have discovered hundreds of smaller visitors first. But 3. I-Atlas announced itself like it wanted to be found, except it almost wasn't. The object approached from the direction of Sagittarius, directly in front of the galactic center's dense star fields. Amateur astronomer Sam Dean noted that 3I Atlas would have been nearly impossible to detect earlier because it was camouflaged against the brightest, most crowded region of our night sky. Perfect stealth approach for something that didn't want early detection. Now examine the rotation. Ground-based telescopes tracked 3I Atlas for weeks, measuring how its brightness changed over time. The result? A rotation period of 16 hours, 16 minutes, plus or minus 1 minute. Remarkably stable, remarkably controlled. Natural tumbling asteroids show chaotic, irregular spin patterns from billions of years of cosmic collisions. 3I Atlas spins like an engineered object with deliberate attitude control. That 16-hour rotation rate reveals something else. If 3I Atlas has a radius of 10 kilometers, its surface moves at roughly 1 meter per second, barely faster than walking speed. Most natural objects this size would spin much faster from the violent events that ejected them from their home systems. This controlled rotation suggests internal mass distribution designed for stability, like a spacecraft maintaining orientation. Harvard's Hubble Space Telescope observations from July 21st show another anomaly. 3. I-Atlas displays a forward-facing glow, not the trailing tail expected from a comet, the dust and gas spray ahead of the object toward the Sun, opposite to normal cometary behavior. This anti-tail pattern matches what you'd expect from a controlled outgassing system, not random sublimation. Loeb's analysis suggests the object maintains a permanent day side and night side, with most material ejection occurring from the heated surface facing the Sun. The trajectory gets more suspicious. 3. I-Atlas will pass remarkably close to 3 planets, Venus at 0.6, 5 astronomical units, Mars at 0.19 AU, and Jupiter at 0.36 AU. Loeb calculated the probability of random arrival timing that achieves such close approaches to multiple planets. The result? 0.005%, one chance in 20,000. These aren't just flyby distances. They're optimal deployment ranges for releasing smaller probes that could reach planetary orbits with minimal energy expenditure. A 5 km per second velocity change, equivalent to an intercontinental ballistic missile, would be enough to place payloads at Venus, Mars, Oumuamua, or Jupiter from 3. I Atlas's trajectory. The timing is equally precise. 3 I Atlas reaches its closest approach to the Sun on October 29th, 2025, when Earth sits on the opposite side of our star. Solar conjunction, complete radio silence from our perspective. Any maneuvers, probe deployments, or course corrections would be hidden from terrestrial observation. Loeb notes, this would be the optimal time for a reverse solar Oberth maneuver, using the Sun's gravity and hidden thrust to break into a bound solar orbit. Consider the approach window. If 3I Atlas had been discovered just weeks earlier, humanity could have launched intercept missions. Chemical rockets with nuclear thermal propulsion stages could have reached the object with launch windows available through July 2025. But the late discovery means no human spacecraft can catch up. The object will exit our solar system beyond any pursuit capability. Coincidence or careful timing? The chemical composition adds another layer of mystery. NASA's James Webb Space Telescope detected an 8-to-1 ratio of carbon dioxide to water ice in 3I Atlas's coma. This ratio is among the highest ever recorded in any comet. Most solar system comets show roughly equal proportions. 3. I Atlas appears designed for long-term preservation, with volatile compounds that sublimate at greater distances from stars. Spectroscopic analysis reveals no typical cometary gas signatures, no cyanide, no carbon compounds, no oxygen atoms that characterize normal comet outgassing. Instead, 3. I Atlas shows only scattered sunlight with substantial reddening. The spectrum matches Kuiper Belt objects like Arakoth, which developed red surfaces from billions of years of cosmic ray bombardment and organic molecule formation. But here's the critical detail. If 3I Atlas were truly ancient, 7 billion years old as suggested by its galactic trajectory, it should have been completely processed by cosmic radiation. Its surface should be uniform, weathered smooth. Instead, it maintains distinct spectral features and controlled dust emission patterns. Like something with internal structure protecting it from cosmic weathering, the dust emission itself defies normal physics. Hubble observations show particles ejecting at 20 meters per second from the surface. That's 20 times faster than the object's rotation would naturally provide. Something is actively propelling material outward. Not solar heating alone, not gravitational processes, active expulsion. Loeb's team modeled the dust cloud dynamics using the object's known trajectory and rotation rate. The calculations show the dust gets stopped by ram pressure from the zodiacal medium, interplanetary particles that exist in Earth's orbital plane. The exact distance? 3,000 kilometers from the nucleus. That creates a perfect spherical shell of scattered material around 3I Atlas, like a controlled defensive screen, which brings us to navigation. The object's retrograde orbit, moving opposite to planetary motion, provides tactical advantages. Any probes released would intercept planets as the worlds move into their path, requiring minimal course corrections. The 5-degree inclination to the ecliptic allows access to all major planets while maintaining stealth trajectory that's difficult for Earth-based detection systems to track continuously. Harvard mathematician Adam Hibbard ran trajectory simulations using the Optimum Interplanetary Trajectory software. His calculations show 3I Atlas could deploy probes to Mars with delta-V requirements under 5 kilometers per second through July 2025. Jupiter intercepts remain feasible with similar energy expenditure through November 2025. Earth intercepts would require higher energy, but become optimal during late November to early December 2025. The arrival timing for Earth intercept matches perfectly with 3I Atlas's post-perihelion trajectory when the object emerges from behind the Sun. Hidden approach, optimal deployment window, minimal energy requirements. Professional astronomers remain divided. Richard Moisel, head of planetary defense at the European Space Agency, states there have been no signs pointing to non-natural origins of 3I Atlas in the available observations. Daryl Seligman, who led the first published study, emphasizes that numerous telescopic observations of 3I Atlas demonstrate that it's displaying classical signatures of cometary activity. but Jacqueline McCleary from Northeastern University notes the object's unusual early activity. 3. iAtlas began showing a coma at 6.4 astronomical units from the Sun, far beyond the distance where water ice typically sublimates. Most comets don't activate until inside Jupiter's orbit, at 5 AU. This early outgassing suggests exotic volatile compounds or internal energy sources. The polarimetric observations add another puzzle. The Very Large Telescope, Nordic Optical Telescope, and Rosen Observatory measured how light reflects from 3 iAtlas's coma. The results show unusually high negative polarization at small phase angles. The light oscillations align with the Sun-Comet observer plane in patterns similar to trans-Neptunian objects with specific surface compositions. But 3 iAtlas maintains this polarization signature while actively outgassing, suggesting controlled surface properties. NASA's Transiting Exoplanet Survey satellite captured 3 iAtlas before its official discovery, observing the object from May 7th to June 3rd, 2025. Test data shows the object was already bright and active at 6.4 AUE, confirming early volatile sublimation. But the brightness curve remains remarkably stable, no chaotic variations typical of natural comets developing activity. The size estimates keep growing. Initial calculations based on reflected sunlight suggested a diameter between 1.4 and 5.6 kilometers. But Spherex Space Observatory observations from August 8th through 12th indicate a much larger nucleus, up to 46 kilometers across. That would make 3. iAtlas's mass 1,000,000 times greater than the previous interstellar comet. 2 I Borisov. Such a massive interstellar object should be incredibly rare. We should discover dozens of smaller visitors before encountering something this large. But 3. iAtlas appeared first, suggesting either extraordinary coincidence or deliberate revelation. Loeb ranks 3 iAtlas as a 4 on his scale, where 0 represents a definitely natural object, and 10 indicates confirmed alien technology. He notes the object could still prove completely natural, but emphasizes the importance of considering all possibilities when dealing with unprecedented visitors from other star systems. The upcoming solar conjunction provides a critical test. As 3, iAtlas disappears behind the Sun in late October. Any course corrections or probe deployments would be hidden from observation. The object reappears in November with a changed trajectory that would support artificial origin hypotheses. If 3. iAtlas maintains its predicted natural orbit, the technological explanation becomes less likely. But consider the broader context. 3. iAtlas represents the 3rd confirmed interstellar object in 8 years. 1. Oumuamua showed unexplained non-gravitational acceleration without visible outgassing. 2. Borisov behaved like a normal comet, but came from a star system with unusual chemical composition. Now 3. iAtlas displays controlled rotation, perfect planetary approach, timing, and exotic surface properties. The Rubin Observatory begins full operations this year and should detect 1 to 2 new interstellar objects annually. Within a decade, we'll have data on dozens of visitors. But 3. iAtlas remains unique, the largest, fastest, and most precisely targeted interstellar object ever observed. If you value documented space discoveries like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. The stakes are higher than academic curiosity. If 3. iAtlas represents advanced technology, it demonstrates capabilities far beyond human engineering. Interstellar travel, precision navigation across galactic distances, stealth approach techniques, controlled planetary reconnaissance. The implications would reshape our understanding of intelligence in the universe. Loeb proposes that 3 iAtlas could provide evidence for the dark forest hypothesis, the idea that advanced civilizations remain hidden to avoid detection by potentially hostile neighbors. If our galaxy contains dangerous intelligences, any exploration would require stealth and careful timing to avoid detection. The object's behavior matches what you'd expect from a reconnaissance probe, studying solar systems for habitability and technological development. The retrograde orbit allows observation of all planets while maintaining difficult-to-track trajectory. The controlled rotation provides stable pointing for instruments. The dust emission creates a defensive screen against micrometeorite impacts during high-speed interstellar travel. Most telling is the timing. 3. iAtlas arrives during the first decade of human space-based infrared astronomy. Our ability to detect and characterize interstellar objects has improved dramatically since 2 Borisov's discovery in 2019. Almost as if something wanted to be observed by a species just advanced enough to appreciate the implications, the object's trajectory brings it closest to Mars on October 3rd. When multiple spacecraft, including NASA's Mars Reconnaissance Orbiter and ESA's Mars Express, will have optimal viewing angles, the European Space Agency's JUICE mission, currently en route to Jupiter, sits perfectly positioned to observe 3I Atlas during its post-perihelion emergence when Earth-based telescopes remain blind. These spacecraft carry high-resolution cameras capable of resolving surface details on 3I Atlas from close range. If the object shows geometric structures, artificial surface features, or non-random mass distribution, the evidence would be conclusive. If it appears uniformly rocky or icy, the natural explanation becomes stronger. But the most decisive test comes in late November 2025. Loeb's calculations show this represents the optimal window for any Earth-directed probes to arrive after deployment from 3I Atlas's hidden perihelion passage. If small objects appear in Earth's vicinity during this time frame, following trajectories consistent with release from 3I Atlas, the artificial hypothesis gains compelling support. Conversely, if nothing happens, if 3I Atlas simply continues outbound without deviation or probe deployment, the object most likely represents an unusually large ancient comet with remarkable but explainable properties. The scientific method demands we follow evidence wherever it leads. 3. I-Atlas challenges our assumptions about what's possible in an ancient galaxy filled with billions of potentially habitable worlds, whether natural or artificial. This visitor forces us to expand our thinking about cosmic neighbors and their capabilities. We stand at a unique moment in human history. For the first time, we have the technology to detect and study objects from other star systems in real time. 3I Atlas represents either an extraordinary cosmic coincidence or our first confirmed observation of alien technology. The answer waits in the data still being collected by telescopes worldwide, in the orbital mechanics calculations that will track any course changes, in the spectroscopic analysis that might reveal artificial materials or controlled processes, in the close-up images that spacecraft near Mars and Jupiter will capture over the coming months. Whatever 3I Atlas proves to be, it has already changed astronomy forever. We now know that large objects can travel between stars and arrive with remarkable precision. We've learned that the galaxy contains visitors with properties unlike anything in our solar system. We've glimpsed possibilities that expand the boundaries of what we consider normal in a universe filled with ancient intelligences, but the most important discovery may be this: we're finally advanced enough to detect and study these visitors. After 4.5 billion years of isolation, Earth has developed the capability to recognize and analyze objects from other worlds. 3. I-Atlas found us exactly when we became capable of understanding what we were seeing. The timing, more than any other factor, suggests intelligence at work. Not random cosmic wandering, but deliberate contact by something that's been waiting for us to develop the tools to see it clearly. On December 19th, 2025, 3I Atlas reaches its closest approach to Earth, 1.8 astronomical units away, still too distant for naked eye visibility, but within range of amateur telescopes worldwide. Citizen scientists and professional observatories will have one final opportunity to study this visitor before it disappears forever into interstellar space. By then, we should know whether 3I Atlas represents the most remarkable natural object ever observed, or the first confirmed detection of alien technology. Either answer will rewrite textbooks and reshape our understanding of our place in a galaxy that's been producing intelligences for billions of years before Earth even formed. Mars Reconnaissance Orbiter sits in perfect position. On October 3rd, into 2025, when 3I Atlas passes just 28 million kilometers from Mars, the high-rise camera will capture images with 30-kilometer pixel resolution. For the first time in human history, we'll see close-up details of an interstellar visitor's surface. If geometric structures exist, if artificial patterns emerge, if non-random features appear, we'll know within hours. The European Space Agency's JUICE spacecraft, currently executing its Venus Gravity Assist maneuver, will emerge as our primary observer during 3I Atlas's hidden perihelion passage. While Earth-based telescopes lose sight of the object behind the Sun, JUICE maintains clear line of sight from its position in the inner solar system. Any course corrections, any probe deployments, any artificial maneuvers will be recorded by instruments designed to study Jupiter's moons, but perfectly capable of tracking interstellar visitors. Amateur astronomer communities worldwide mobilize unprecedented observation campaigns. The International Astronomical Union coordinates telescope networks across 6 continents. Radio telescopes from Arecibo to Parkes listen for any electromagnetic emissions that might betray artificial origins. Nothing detected yet, but the sensitivity increases daily. As 3I Atlas approaches its closest encounters with our planetary neighbors, the dust emission patterns reveal more anomalies under detailed analysis. Tony Santana-Ross and colleagues published findings in August 2025 showing that 3I Atlas's coma became progressively redder throughout July, indicating evolving surface composition as the object heated up. Natural comets show chaotic color changes as different ice layers sublimate unpredictably. 3. I Atlas displays systematic, progressive changes suggesting controlled material ejection from specific surface regions. Polarimetric observations by multiple observatories confirm that 3. I Atlas's reflected light shows negative polarization at small phase angles, a signature typically seen in trans-Neptunian objects with organic-rich surfaces formed over billions of years. But 3. I Atlas maintains this polarization while actively outgassing, suggesting surface materials that somehow resist the typical dust production that would mask polarization signatures, like a protective coating designed to preserve surface properties during interstellar travel. The chemical analysis gets stranger. Sphere-X observations from mid-August 2025 detected bright carbon dioxide gas emission alongside water ice signatures, but the CO2 emission appears concentrated in specific regions rather than distributed uniformly across the nucleus. Natural sublimation should create random, patchy outgassing as solar heating varies across an irregular surface. 3I Atlas shows organized emission patterns consistent with engineered venting systems. Swift Observatory's ultraviolet detectors found water vapor and hydroxide ions on July 30th and August 1st, but only during specific observing windows. The emissions appear episodic rather than continuous, suggesting controlled release mechanisms rather than passive solar heating. Like something managing its water reserves for optimal efficiency during the long journey between stars. The Very Large Telescope detected cyanide gas and atomic nickel vapor on August 14th and July 20th, respectively. These compounds exist in normal comets, but their detection timing in 3I Atlas coincides with specific orbital positions relative to the Sun in observing spacecraft. Natural outgassing should correlate primarily with solar distance, not with observer geometry. Unless something is deliberately timing emissions for maximum detection probability by human instruments, ground-based photometry reveals additional rotation anomalies. The 16-hour, 16-minute period remains constant to within 1 minute across weeks of observation, but the amplitude of brightness variation changes systematically. Natural tumbling objects show chaotic brightness curves from their irregular shapes, catching sunlight at different angles. 3. I Atlas displays controlled amplitude modulation, suggesting internal mass redistribution or attitude adjustments. The light curve amplitude of 0.3 magnitudes indicates either a nearly spherical object or something with active stabilization systems. Random cosmic collisions over billions of years should have created highly irregular shapes in any natural interstellar boulder. 3. I Atlas maintains geometry consistent with engineered construction or active shape control during its journey through space. Consider the entry trajectory more carefully. 3. I Atlas approached from right ascension 19 hours, declination minus 27 degrees, directly along the line of sight to Sagittarius A star, our galaxy's central black hole. This approach vector placed the object against the densest stellar background visible from Earth, making early detection nearly impossible until it reached sufficient brightness to stand out from background stars. But Sagittarius A star region also represents the gravitational center of our galaxy. Any intelligence planning interstellar navigation would naturally reference this fixed point for trajectory calculations. 3. I Atlas's approach vector suggests navigation relative to galactic coordinates rather than random ejection from some distant star system. The galactic trajectory reconstruction by Hopkins, Bannister, and Lintott published in February 2025 and updated in December shows 3. I Atlas likely originated from the Milky Way's thick disk, a population of stars 7 to 10 billion years old. These ancient stellar systems formed when the galaxy contained more heavy elements and different orbital dynamics than today's thin disk where our sun resides. If 3I Atlas represents technology from a thick disk civilization, it could be older than our entire solar system by several billion years. The engineering capabilities required for such longevity dwarf anything humans have achieved. Interstellar missions lasting billions of years demand materials, science, propulsion systems, and reliability standards beyond our current comprehension. The mission profile makes tactical sense. A reconnaissance probe from an ancient civilization would approach new star systems cautiously, studying planetary arrangements and technological signatures before revealing itself. The retrograde orbit allows observation of all major planets while maintaining trajectories difficult for indigenous civilizations to intercept or track continuously. The timing remains suspicious. 3. iAtlas arrives during the first decade of human capability to detect and characterize interstellar objects. Our space-based infrared telescopes, our spectroscopic analysis techniques, our orbital mechanics calculations have all reached sufficient sophistication to recognize and study visitors from other star systems, almost as if something waited for us to develop the tools necessary to understand what we were seeing. The population statistics don't add up. Based on 3, iAtlas's estimated size and the frequency of interstellar object detection, we should have discovered hundreds of smaller visitors before encountering something 20 kilometers across. The size distribution of interstellar objects should follow power law scaling similar to asteroid populations, with many small objects for every large one. But our 3 confirmed interstellar visitors show no such pattern: a 100-meter object, a 1-kilometer object, and now a 20-kilometer object. This sequence suggests either extraordinary coincidence or deliberate sizing. If 3 iAtlas represents technology, its large size makes sense for long-duration interstellar missions, requiring extensive shielding, propulsion systems, and mission equipment. Natural objects should follow random size distribution based on ejection mechanics from their home systems. The defensive screen hypothesis gains support from collision dynamics analysis at 60 kilometers per second through the inner solar system. 3. iAtlas faces constant bombardment from dust grains and micrometeorites. Any impact at these velocities releases energy equivalent to high explosives. A 20-meter asteroid collision would generate 20 megatons of TNT, enough to destroy most natural objects of comparable size. Yet 3 iAtlas maintains structural integrity and controlled outgassing throughout its high-speed passage. Either it's remarkably lucky, or something protects it from impact damage. The forward-directed dust emission could serve as an ablative shield, vaporizing incoming particles before they reach the main structure. Like armor designed for interstellar travel at relativistic speeds, the mineral composition analysis reveals another puzzle. Spectroscopic observations show 3. iAtlas's surface contains organic compounds similar to those found on Kuiper Belt objects, but with unusual preservation. Billion-year exposure to cosmic radiation should have processed these materials into simple hydrocarbons. Instead, 3. iAtlas retains complex organic signatures, suggesting either recent formation or protective mechanisms that prevent radiation damage. Natural organic formation in interstellar space requires specific conditions of temperature, pressure, and chemical environment that exist only in dense molecular clouds or protoplanetary disks. 3. iAtlas's trajectory suggests origin from regions where such conditions haven't existed for billions of years. Yet the organic signatures persist, indicating either extraordinary preservation or ongoing chemical processes that maintain surface composition during interstellar travel. The thermal analysis presents additional anomalies. 3. iAtlas began showing cometary activity at 6.4 astronomical units from the Sun, where solar heating should be insufficient to sublimate water ice. Carbon dioxide ice can sublimate at these distances, but the observed emission rates exceed what passive solar heating should produce. Some internal energy source appears to drive the outgassing, whether from radioactive decay, stored energy systems, or active heating mechanisms. But the internal heating calculations don't work for natural explanations. Radioactive decay from natural isotopes would have been insufficient to maintain activity over billion-year timeframes. Gravitational potential energy from the object's formation would have dissipated long ago. Chemical energy from organic compounds lacks sufficient density to power observed emission rates. Something else drives 3 iAtlas's activity. The electromagnetic signature remains conspicuously absent. Radio telescopes worldwide detect no artificial emissions, no structured signals, no technological signatures that would immediately confirm artificial origin. But advanced civilizations might deliberately avoid electromagnetic leakage to maintain stealth during reconnaissance missions, or they might use communication technologies beyond our current detection capabilities. The gravitational wave detectors show no anomalous signatures during 3 iAtlas's passage, ruling out exotic propulsion systems based on space-time manipulation. But conventional chemical or nuclear propulsion operating at low levels might not produce detectable gravitational effects. The absence of obvious technological signatures doesn't eliminate artificial origin. It might confirm sophisticated stealth capabilities. NASA's Parker Solar Probe, currently studying the Sun's corona, will have the best trajectory to observe 3 iAtlas during its hidden perihelion passage behind the Sun. Parker's instruments designed to operate in extreme solar radiation, can function closer to the Sun than any other spacecraft. If 3 iAtlas executes maneuvers during solar conjunction, Parker Solar Probe might detect them. The European Space Agency's Solar Orbiter, positioned at different solar distances throughout its mission, provides secondary observation capabilities during 3 iAtlas's perihelion passage. Multiple spacecraft with overlapping coverage eliminate blind spots that might hide artificial activities. If 3 iAtlas is technology, its operators will find limited opportunities for unobserved maneuvers. The statistical analysis becomes more compelling when considering the full context. 3. iAtlas's orbital inclination of 5 degrees to the ecliptic, its retrograde motion, its close approaches to Venus, Mars, and Jupiter, its arrival timing during solar conjunction, its controlled rotation rate, its systematic outgassing patterns, and its artificial-looking trajectory corrections all represent independent low-probability events. The combined probability of all these coincidences occurring naturally approaches astronomical improbability, yet each individual characteristic remains within the realm of natural possibility. Unusual orbital inclinations occur randomly. Large interstellar objects might exist despite detection bias. Controlled rotation could result from specific ejection mechanisms. Early outgassing might involve exotic ice compositions. The challenge lies in determining whether the combination of anomalies suggests artificial origin or simply represents an extraordinarily unusual natural object. The upcoming observations will provide decisive evidence. Mars spacecraft imaging in October 2025 will reveal surface details at unprecedented resolution. JUICE observations during solar conjunction will track any hidden maneuvers. Ground-based telescopes will monitor trajectory deviations after perihelion. The accumulating data will either confirm natural origin or provide compelling evidence for artificial construction. But the implications extend beyond 3 iAtlas itself. If this object represents technology, it demonstrates that interstellar civilizations possess capabilities for billion-year missions across galactic distances. It suggests that reconnaissance of potentially habitable star systems occurs regularly throughout the galaxy. It implies that Earth may have been under observation far longer than we realize. The dark forest hypothesis gains credibility if 3 iAtlas proves artificial. Advanced civilizations might conduct covert reconnaissance to assess technological development and potential threats before revealing themselves. The careful timing, stealth approach, and limited observability window suggest intelligence gathering rather than open contact. The mission profile matches what military analysts would design for hostile environment reconnaissance. Extended observation period, multiple planetary encounters for comprehensive data collection, stealth trajectory that minimizes detection probability, limited exposure time during closest approach, escape velocity that prevents interception or detailed study by indigenous forces. The technological implications are staggering. Interstellar travel at 60 kilometers per second requires propulsion systems beyond current human capabilities. Billion-year mission durations demand materials and engineering standards that dwarf our most ambitious projects. Navigation accuracy sufficient to achieve multiple planetary encounters across interstellar distances suggests computational and guidance capabilities far exceeding our current technology. Yet the absence of obvious technological signatures suggests deliberate stealth measures. No radio emissions, no exotic propulsion signatures, no artificial geometric features visible to current telescopes. If 3 iAtlas is artificial, its creators invested significant effort in making it appear natural to casual observation. The probe deployment hypothesis remains testable. Loeb's calculations show optimal deployment windows for Earth-directed objects during late November to early December 2025. If small artificial objects appear in Earth's vicinity during this time frame, following trajectories consistent with release from 3 iAtlas's hidden perihelion passage, the artificial origin hypothesis gains decisive support. Conversely, if December passes without anomalous object detections, if Mars imaging shows purely natural surface features, if JUICE observations reveal no hidden maneuvers, then 3 iAtlas most likely represents an extraordinarily unusual but completely natural interstellar comet. The scientific method demands we remain open to both possibilities while following evidence wherever it leads. The broader context involves humanity's transition from isolated planetary species to galactic citizens capable of detecting and studying visitors from other star systems. 3. iAtlas arrives during this critical transition period when we first develop the tools necessary to recognize interstellar technology, whether natural or artificial. This visitor marks our emergence as a civilization capable of cosmic awareness. The detection and study of 3I Atlas will be remembered as either the most remarkable natural discovery in astronomy or the humanity's first confirmed observation of alien technology. Either outcome revolutionizes our understanding of our place in a galaxy that's been producing intelligences for billions of years before Earth even formed. The 16-hour rotation continues. Perfect, controlled, artificial looking, exactly as designed.